Alright, so hello, my name is Kreulach. I'm going to be presenting for part of my project in EEL6825 Pattern Recognition. I'm going to be talking about different image-to-image translation methods and solutions to this problem. There are a whole variety of different methods present. I'm going to be discussing generative adversarial networks, variational autoencoders, and diffusion models broadly, and GANs and diffusion models in specific. My code covers very particularly CycleGAN, which is a special implementation of GANs. Moving on. So what is image-to-image translation? Image-to-image translation is a very broad collection of different things you can, like different operations you can perform on images, but in this particular case, the problem we want to solve is given two classes of image, A and B. Then, given an image of class A, we want to create a new image with the structure from A but the style of B. Now, style, image class, and structure are all sort of fuzzy words, so I'm going to spend a bit of time talking about what that means, with the example being these zebra and horse images in the middle of the screen. So, in the top example, you can see on the left, image class A is zebra, and image class B is horse. So, you have these, in the fake image, which is two horses now, supposedly, they're in the same pose, they're on the same background. That is the structure element, and the style element is the fact that the horse-like objects are now painted brown. That is what is meant by preserving structure and applying style. It's functionally still the image from class A, but now it could pass as an example of image class B. And then below, you can see the same story plays out, where it's the same Mustang in the same field, except now we've painted stripes onto the Mustang. And of particular interest, or at least to me with this problem, it's fun to notice that the GANs tend not to catch the fact that the zebra tails and horse tails are very different, actually, and they end up with horses with zebra tails and zebra ears, and zebras with horse tails after the conversion. Anyway, another thing to notice is that in the backgrounds on the zebra and horse examples, ideally the only thing the GAN is supposed to change is the actual horse-like objects, that is to say the zebras or horses, but it also makes small alterations to the background, and that's just the nature of how GANs are trained and how they perform. But you can see in other examples where you're trying to do a full scene repainting, that is to say, for example, the Monet to Photos example, that's where the term style comes from, wherein you're actually trying to fully repaint the image in a different artistic vision, or, in the case of summer-winter, seasonal palette. But ultimately, the terms style and structure are maintained in various places in the literature. So, moving on to the methods used to accomplish this. So, three of the main methods are diffusion, variational autoencoders, and generative adversarial networks. And they all have certain trade-offs present in what's called the trilemma, where diffusion models generally produce high-quality samples and have a broad variety of output, but they generally take a longer time to sample due to a casualty of the MCMC methods. And as mentioned here, and as you can see from the graph yourself, GANs produce high quality samples, and they produce them quickly, but they suffer from mode collapse, something I'll go into more later. And VAEs, I won't be talking about them much, but in short, they don't produce terribly good samples. So onward to what is a GAN. So generative adversarial networks essentially take the problem of generating images that resemble a class and turn it into a competition between a discriminator and a generator. The generator creates fake candidate images that it believes, or that it is attempting to make resemble the original images, and then the discriminator receives both real examples from the training data and fake examples created by the generator, and it classifies them as either real or fake. And this creates an adversarial zero-sum game, wherein the discriminator wants to classify as many of these samples accurately as possible. That is, specifically, it wants to classify fakes as fake, and the generator wants the discriminator to fail and classify as many fakes as real as possible. And so that is how their two loss functions combine to ideally make the two improve each other. And here on the right you can see just sort of some examples of GAN output, wherein they're trying to convert cats to dogs, humans to cats, and anime-fi women. What a time to be alive. So the architecture of a GAN, more of what I was talking about and how the discriminator and generator relate to each other. So the generator is fed random noise from the latent space, usually, generates an image, at which point it is compared by the discriminator to a real image, it's judged by the discriminator, and then based on the performance of the discriminator, its error is used to update both the discriminator and the generator. This leads to several problems with GANs, which is when one of the two gets too good at its job. If the discriminator is ever too successful and manages to successfully or regularly discriminate correctly, all of the fake images it manages to pick out and say are fake, and all of the real images it knows are real, then the generator doesn't get very much useful feedback on which to improve. None of its samples were determined to be good and worthy of iterating on. And similarly, if the generator gets too good and successfully finds one or a small number of very good images that the discriminator just can't seem to figure out are fake, then the generator can very quickly collapse into just producing that one image or very small variations on that image and receiving very high scores because the discriminator can't tell. But ultimately, both the generator and the discriminator in this situation are not very good. So this exact relationship where the game can become one-sided leads to a common problem with convergence, which is that it's very difficult to tell when to stop training, and it's very difficult to tell if you've gone too far, if you haven't gone far enough, if it's fallen into one of these errors and it'll essentially never recover. And it's also just very difficult to tell when it started generating good output. So when you're training GANs, there's a whole selection of tips and tricks to try to avoid these problems, but ultimately they're just baked into the model, and they're a thing you have to learn to struggle with. So diffusion models, the other thing I'd like to compare GANs to. They're a more recent innovation. They were first arriving in 2015, but they've become significantly more popular as of a couple years back, 2020. And diffusion models basically work by taking the training data and corrupting it step by step by adding Gaussian noise, and then training a Markov model to reverse that same process of slowly removing noise and extracting a image similar to presumably your training data. It's like that line about carving marble sculptures. You don't try to create something, you just remove what is wrong. So the process is essentially forward a Markov chain of increasing Gaussian noise. Each step you add more noise. The first steps are relatively small edits, and then eventually you're adding just blasts of noise that will hopefully reduce it to complete meaninglessness. And then backward, you're trying to learn how to take this noise and slowly carve away at whatever type of image you want to produce. Or if it's not an image problem, for example, with this spiral, it's a similar procedure, but ultimately with a different goal. So the advantages and disadvantages of diffusion models. On the pro side, you have it produces high quality samples, and because it has actually a very large latent space, there are an incredibly large number of parameters in the model that can be tuned. It produces a very large diversity of output. It doesn't suffer from mode collapse in the same way that the GANs do. But on the other side of that coin, the diffusion models generally sample very slowly as a consequence of the Markov model necessary to produce a sample going back from Gaussian noise. Each of those steps is relatively costly, especially when you want many steps in order to produce good output reliably. And also, a secondary casualty of that very large latent space is that there are a whole bunch of different variables to optimize, and there aren't necessarily strong methods for how to pick all of the parameters of the model. And it can be fairly expensive to try to explore them. Alright, so that's diffusion models and GANs, and a quick overview of just sort of what I was working on. I'm going to do a couple more things real quick. First, I would like to show this little video of a diffusion model working. This is for super resolution specifically, where you give it a low resolution example and then you run it on a higher resolution output with the goal that it would ideally create a higher resolution version of the same image. And I find the output fairly convincing. It's a really cool method. I'm a big fan of diffusion models, to be honest. But anyway, so I just wanted to show that really quick. And then the performance of my code. Here you have in my project, PyTorch, CycleGAN, run my test code, data root, datasets. It'll then generate approximately 50 processed versions, and this should be zebras from horses. Let me pull that up really quick. It should be in results, horse to zebra, test latest images, and then here are some examples, yes, thank you, of zebrified horses. So here's the original horses, and here is the zebrified version. And there's a bunch more like it, with some very interesting, where you can kind of see the head got completely obliterated there. Anyway, so that is the sum of my presentation. I apologize if there were any background noises, but all right. Have a good night.